Hi, welcome back. We're up to lecture 17, the second to last lecture of the course. And in lecture 17, we'll cover mixed factorial ANOVA. This lecture is organized into two segments. In the first segment, we'll just cover what's new in a mixed factorial. You might be thinking, well, we've done several ANOVA designs. We've done factorial ANOVA, but there are several new concepts and things to consider when you have a mixed design. So we'll talk about those in the first segment. In the second segment, we will do an example and we'll walk through it in R so that you can see how repeated measures works and how mixed factorial works in R. So just to be clear, a mixed factorial design, what I mean here is still a factorial ANOVA, not a mixed level design. That's something different. More advanced technique, sort of beyond statistics 1. So we're still just doing an ANOVA. The trick is that here we have two independent variables like the factorial case, but one is manipulated between groups and the other is manipulated within groups, or it's a repeated measures variable. So here's what the data structure would look like. In sort of most common data structures for a 3x3 mixed. And common notation is like this. For the first independent variable, we use letter A. For the second, B. And B here is the independent variable that's manipulated within groups. That's the repeated measure. So it's in the parentheses with S, which stands for subjects. And a common data structure is like this, where A, the between groups variable, is represented in one column, and the different levels of B are represented across columns, again, to keep one row per subject. But again, that's not how R does it. And in R, this 3x3 structure would look like this. Okay? Again, it's not that big of a deal. It's just you need to know that, obviously. You need to know the structure of your data before you can do the ANOVA. So what's new? We've done ANOVA, we've done factorial ANOVA. You'll see a lot's new. Partitioning the sums of squares looks a little different. The formulas for the F ratios are different. The error terms are different. And how you approach simple effects analyses is slightly different. You just have to make a decision which way to go and just be careful about using the right error term. And then there's one more assumption that we need to consider. So let's walk through these. Here's the partitioning of sums of squares using a Venn diagram again. So just like the factorial case, we have the systematic effects here. That's main effect of A, main effect of B, and the interaction A by B. Notice we have two error terms now. Right? That's because we have both a between variable and a within. So here, this is the error term for the between groups ANOVA, right? S with an A. That's just within subjects variance. So when we look at the main effect of A, that's going to be our error term. But then we have this other portion of unsystematic variance for the within groups. It's B by S. But we have to acknowledge that subjects are embedded in conditions A. So it's not just B by S, it's B by S with an A. Degrees of freedom calculations are always easy. Here they are, just the number of levels minus 1 for each of the main effects. Any interactions, the product. So I'll just zip through that. Mean squares, again, really easy. It's always just sums of squares over degrees of freedom. And now we have three F ratios, main effect of A, main effect of B, interaction. But notice we have those two different error terms. As I said, when we're partitioning the sums of squares, if we're just looking at the main effect of A, then that's like doing a one-way between groups ANOVA. If we're just looking at the main effect of B, that's like doing a one-way repeated. And then the interaction uses that same error term as the repeated. We can do post hoc tests just like we did in one-way ANOVAs. So if we're looking at post hoc tests on main effects, then you just proceed as if you're doing a one-way between, if it's the between, if it's A. So for example, we could use Tukey's test. If you're doing the post hoc test to follow up a main effect of B, then that's real easy. Just do what we did when we did a repeated measures ANOVA. Do pairwise comparisons, but adjust your p-value with that Bonferroni correction. If you have a significant interaction, remember you need to do simple effects analyses to isolate the locus of the interaction. And there's always two options on how to pursue this. So you can either do the simple effects of the between groups IV at each level of the repeated measure, or you could do the simple effects of the repeated IV for each group, A1, A2, A3, so on. You should just choose one or the other. Typically, one way makes more sense theoretically in terms of telling your story. You shouldn't do both. To do both is redundant, and then the results section of a paper or a presentation gets really long-winded. So just pick one, and again, the point of this is just to explain why there's an interaction if there is. Again, to make that clear, the data structure might look like this. If I want to do the simple effects of the between subjects IV, then I would be looking at the effect of A at each level of B. That's what simple effects are, the effects of one independent variable at a particular level of the other. So if I wanted to do the simple effects of A at each level of B, then I'd just be doing a series of one-way between groups ANOVAs. If I took the other path, if I wanted to look at the simple effects of B at each level of A, then I'd just be doing a series of one-way repeated measures ANOVAs. That is, I'd just be looking at within A1, what's the effect of B? Within A2, what's the effect of B? And so on. Okay? So you just have to pick one, and then you proceed as if you're doing one-way ANOVAs, either between or within, depending on which path you chose. And that's articulated here. Here are the formulas. Of course, you're not going to do this by hand. You can just implement it in R. But here are the formulas. So this is if you chose to do the simple effects of the between groups IV. So the simple effect of A at each level of B. The way I'd write that is f of A at B1, for example, is mean squares A at B1, and mean squares S within A at B1. You could then follow that up by doing simple comparisons. And because you're doing this on a between groups IV, the simple comparisons, or the post hoc tests, right, they all use that same error term, assuming homogeneity of variance. If we do it on the repeated measures IV, then I look at the simple effect of B at each level of A. So the effect of B at A1, and the effect of B at A2, and so on. And notice it's an interaction term down here and there. It's B by S, because we're doing a repeated measures. Let's move on to the assumptions. So to be clear, each subject is contributing B scores, because I'm using B to refer to the within subjects variable. So in this example that the data structure example, there were 3 levels of B. So I would have 3 scores for each individual subject. What that means is there are B variances. There are 3 in this case. What that also means then is we can look at how many covariances there are. So if there are 3, then we can have 3 covariances. If we had 4 levels of B, we'd have 6 covariances, and so on. Here's a formula to calculate that. It's just the number of unique entries in the covariance matrix. So there are a couple assumptions here. One is the between groups assumptions. This one you know about already. It's just the Levene's test is used to test the homogeneity of variance assumption. But then there's another one. And this shouldn't be surprising. We could look at the homogeneity of covariance. Because again, we have multiple scores from each subject, and there are different subjects across groups. So we could look at the extent to which the covariances are consistent or not across conditions. So to make that more clear, let's look at this illustration. What we're going to use is Box's test. That's the statistical test used to test to see if these covariance matrices are equivalent or not. So the null hypothesis is that there's no difference between these 3 covariance matrices. And I have one for each of my between groups conditions. And in these matrices, I could represent the covariances. Okay? The assumption is that the covariances across conditions are about the same. If that's violated, you run the risk of increasing the probability of a type 1 error. So again, there are these adjustments that have been made a long time ago by statisticians, Greenhouse, Geyser, Wynne-Felt. They're available in R. But alternatively, you might just take a new look at your data. That might be an interesting effect. There might be really something interesting going on. And if you think about this, this is exactly what we did way back in multiple regression when we did moderation analysis, right? It's saying there is a correlation in here that changes as we go from like A1 to A2, right? That would be like A is moderating the relationship between B1 and B2, for example. So you could do a moderation analysis in multiple regression, and we did that. So you might want to just take a whole new approach to your data if you find that. And finally, there's the within subjects assumption. Again, same as before, there's the sphericity assumption, so nothing new there. So to sum up the first segment, mixed factorial design, it just means we have two independent variables, one's manipulated between, one's manipulated within. So what's new? Well, the partitioning of sums of squares looked a little different because we have two different error terms, so you have to know which one to use when. You really have to be careful about that. The formulas change slightly, but there's still just 3 F ratios because we're just dealing with a factorial ANOVA. Again, be careful about your error terms for your post-hoc tests, and be careful about your approach to the simple effects. And then remember, there's one new assumption, that's the homogeneity of covariance, and we can test for that using Box's tests.